Henry's law is a gas law that applies to closed systems and dilute solutions. It states that at a constant temperature, the solubility of a gas in a liquid is proportional to the partial pressure of the gas above the liquid. In this video, a gas is in equilibrium between the liquid and gas phases. When the gas is compressed, the solubility of the gas in the liquid increases proportionally with the increase in pressure. The equation shown is for Henry's law, relating the partial pressure of the gas to the concentration in the solute with the constant K. That constant is Henry's constant, which is different for each gas and varies with temperature. The table shown lists some values of Henry's constant for selected substances.
An example of Henry's constant in the real world is that Henry's constant is used in Wisconsin legislative documents for defining hazardous waste. According to the state's hazardous waste regulations, they apply to compounds with Henry's constant with a mole fraction of at least 0.1. This same rule was found in other states' legislation as well. This is because the larger the Henry's constant, the more volatile the chemical is. For an example problem, the solubility of naphthalene is 31 milligrams per liter, and the vapor pressure is 0.2336 millimeters of mercury. Find Henry's constant for naphthalene and determine if it's a hazardous waste at 25 degrees Celsius. So we'll start with Henry's law of P equals Kx. First, we need to take the solubility of naphthalene and convert that from milligrams per liter to moles per liter. Using the molecular weight of naphthalene as 128 grams, we get a mole fraction of 0.000242 moles per liter. Using the ideal gas law combined with Henry's law and the volume equaling 1 liter, we get P equals K over XRT. Using an R of 0.0821 liters ATM per mole K, we have to convert our pressure to ATM first. And this is by going 0.2336 divided by 760 millimeters of mercury. To solve this problem, we use Henry's law of P equals Kx. First, we must convert the solubility of naphthalene from milligrams per liter to moles per liter. We do this using the molecular weight of naphthalene, C10H8, which is 128 grams. We get a solubility of 0.000242 moles per liter. Then, combining the ideal gas law to Henry's law to convert for temperature, we get a volume of 1 liter, so we get P equals K over KXRT. The ideal gas law and Henry's law to combine and convert for temperature, we get a volume of 1 liter, so P equals KXRT. With an R of 0.0821 liters ATM per mole K, we need to convert the vapor pressure of millimeters of mercury to atmospheres. This is using the conversion of 1 atmosphere to 760 millimeters of mercury. This gives us a vapor pressure of 0.000307 atmospheres. Plugging this into our equation, P equals KXRT, we get a K value of 0.051. According to the legislature, of a hazardous waste being considered greater than 0.1 Henry's constant mole fraction, our K is less than 0.1, so it is not considered a hazardous waste.
An example of when to use Henry's constant is to find the mass in grams of dissolved carbon dioxide in a 1 liter bottle of carbonated water. We'll have the Henry's constant, assume a pressure of 2.4 atmospheres at 25 degrees Celsius in the bottle, and Henry's constant of 29.76 atmospheres per moles liter at 25 degrees Celsius. A real-world example of something like this is a SodaStream water carbonating device. This device adds carbon dioxide to water, thus making soda pop. To solve this equation, we first start off by writing out the Henry's constant equation, which is pressure equals Henry's constant times the concentration. We know the value of the pressure as 2.4 atm and equals the Henry's constant of 29.76 atm per moles a liter times the concentration. Solving for the concentration, this gives us 0.08 moles a liter of carbon dioxide. We know that we have 1 liter of solution. This times the concentration will give us 0.08 total moles of carbon dioxide in the 1 liter water. We're now going to find the molecular weight of carbon dioxide, which is 12 plus 16 times 2 for carbon and the 2 oxygen, giving us a total molecular weight of the carbon dioxide of 44 grams per mole. Now taking this value times the 0.08 moles in the water, we get the total grams of the carbon dioxide in the water equals 3.5 grams.
Decompression sickness is also known as the bends, which describes a condition arising from dissolved gases coming out of solution into bubbles inside of the body on depressurization. This can occur at high altitudes and large underwater depths. The risk of decompression sickness increases when diving for extended periods or at even greater depths, without ascending gradually and making decompression stops needed to slowly reduce the excess pressure of inert gases dissolved in the body. There are 2 important factors to consider when practicing diving safety. The first, the rate and duration of gas absorption under pressure, which is to say, the deeper or longer the dive, the more gas absorbed into the body tissue in higher concentrations than normal. The second is the rate and duration of outgassing on depressurization, which is to say, the faster the ascent and the shorter the intervals between diving stops, the less time there is for absorbed gas to be offloaded safely through the lungs, causing these gases to come out of solution and form microbubbles in the blood, which can be dangerous. In this calculation, we're trying to find the difference in solubility at different underwater depths that a scuba diver may encounter. The first calculation is finding the pressure of nitrogen in air at 40 meters underwater using the partial pressure calculation and summing this with the pressure head of the water column. Then, Henry's law is used to find the amount of gaseous nitrogen that can dissolve into water. The same steps are repeated for the depth of 70 meters. To show how the solubility of nitrogen changes from 40 meters to 70 meters underwater, the difference is taken. As we can see, there is a considerable amount of change in the concentrations. This means that there can be as much as 38% more nitrogen in your body at 70 meters underwater than at 40 meters underwater. This excess amount of nitrogen is what comes out of solution as microbubbles.
Thermal pollution occurs when there is a man-made entity that is using water as a coolant and discharging this excess heat into the environment. Elevated temperature in bodies of water decrease the level of dissolved oxygen in water. This can harm aquatic animals such as fish, amphibians, and other aquatic organisms. Thermal pollution may also increase the metabolic rate of aquatic animals as enzyme activity increases, resulting in these organisms consuming more food in a shorter amount of time. This increased metabolic rate may result in fewer resources in the environment. The more adapted organisms moving in may have an advantage over organisms that are not used to the warmer temperature. This can kill off certain aquatic life and lead to an imbalance in the ecosystem. Also, high temperature limits oxygen dispersion into deep waters, contributing to anaerobic conditions. This can lead to increased bacteria levels when there is an ample food supply.